Hello, and welcome to the Chapter 3.3 online lecture on modeling with systems of first-order differential equations. So a system of ordinary differential equations is two or more differential equations involving functions of a single common independent variable. So for example, if y and u are both functions of x, the following is a system of differential equations. So both y and u are functions of x, and we have this relationship, y prime is y plus 4u, and u prime is 2y plus 3u. So the derivative of each function is a function of not only the original function, but also the other function. The general solution to this happens to be this. Back in the 1.1 lecture, we verified that these two do indeed satisfy both of these equations simultaneously by plugging in. So here's a nice introductory example to a system of differential equations. So in a radioactive decay series, we can have one element decay into another, which decays into another, etc. So suppose that there are three elements x, y, and z, which decay respectively into each other. So x decays into y, which decays into z. Each of these has a different decay rate. For example, uranium is quite stable, relatively speaking. So dx dt, the decay rate of the first element, would be equal to negative lambda 1x, where this negative lambda 1, that's just the proportionality constant, and by custom, we say that it's negative, where this negative lambda 1 is just the proportionality constant, and by custom, we put a negative sign because the amount of x is decreasing, and that way lambda 1 is a positive number. So element x decays into y. So it's decreasing at this rate, and meanwhile y is increasing at the rate lambda 1x, because x is decaying into it, but meanwhile y is itself radioactive with a different radioactivity proportionality constant, lambda 2y, so it's increasing from element x decaying into it and decreasing because it is itself radioactive. And then meanwhile our third element, z, into which y decays, that is just increasing at the rate lambda 2y, because for every amount of y that decays, it becomes z. So what we wind up with is this system here of differential equations. So here's the system of differential equations that we got. And this type of system of differential equations can be solved by successive solving and substitution. So for example, this first differential equation, that's just x, that's just relating dx dt to x itself. So we could solve for x there, and then plug that in for x over here, and so forth, and successively solve this system. We won't be able to do this for more complicated systems, but we can do it for this one. Let's illustrate. Separating variables, that is 1 over x dx is negative lambda 1 dt. We can integrate both sides. Lambda 1 is just a constant, remember. So that's negative lambda 1 t plus c. We take e to the power of both sides, and we have that x is equal to e to the negative lambda 1 t plus c. And then we do our usual rename, and x is ce to the negative lambda 1t. And now that we have that, well, that is x. So we can take that and substitute it into the second equation, and then solve that one. And we'll actually wind up with multiple arbitrary constants. We'll get another one over here. So let's actually call this c that we got here, we'll call it c1. So we got that x is this. Let's take that and plug it in. And this differential equation now becomes dy dt is lambda 1x minus lambda 2y. This is not separable. The right-hand side is not a product of a function of t only and y only. However, it is linear. So separating variables, this is y prime plus lambda 2y is lambda 1 c1 e to the negative lambda 1t. Our integrating factor is e to the integral of p of t dt, which is just e to the lambda 2t. So we multiply both sides by that. And now this is fy prime plus f prime y, which on doing the product rule is fy all prime. So the left-hand side is that, and the right-hand side we can use exponential laws and combine these two. And this is lambda 1 c1 e to the lambda 2 minus lambda 1 t. Since we can add these two together, and then I factored out a t. So far we got that. Now we integrate both sides, dt. That just undoes this derivative on the left side. And on the right side, integrating, we divide by this, and then plus a different arbitrary constant c2. That's why we named that one c1. And these different arbitrary constants, those will correspond to the initial amounts, essentially, of x, y, and z. Okay, so y is thus equal to the following. We'll divide both sides by this. And we wind up with that. Dividing both sides by this, that's the same as multiplying by e to the negative lambda 2t. So over here, that negative lambda 2t will get rid of this lambda 2 there, leaving just that, or this component. And now finally, now that we have this for y, we just need to plug it in there. So this is now dz dt is this. I just multiply that lambda 2 to both pieces. Notice that there's no z on the right-hand side, nor x nor y. This is just saying that the derivative of z is this function of t. So all we do is we integrate both sides, dt. And doing so, well, the integral of dz dt is just z. And the integral of this is, so the first part is this, because we divide by negative lambda 1. It cancels out that lambda 1, and the negative part swaps those two in the denominator. And over here, we divide by negative lambda 2, and that is negative c2 e to the negative lambda 2 t. And then don't forget the plus c3, a third arbitrary constant. So that's our z. And now we have solved for all three functions, x, y, and z. Remember that we also got earlier that y was this. And then the first thing that we got was that x was this. So that is our general solution to this system of differential equations modeling this radioactive decay sequence. And then in practice, we could solve for the arbitrary constants from initial conditions like the initial amount of x, y, and z. And we could solve for lambda 1 and lambda 2 in the same way we solve for the proportionality constant with, for example, a cooling down cup of hot coffee. All right, and another type of scenario where we'll have a system of differential equations is tank mixing, but with two tanks. So suppose that tank A contains 50 gallons of water, in which 25 pounds of salt are dissolved, and tank B contains 50 gallons of pure water. And suppose that they mix according to the depicted flow rates, 4 gallons a minute from A to B, 1 gallon a minute from B to A, 3 gallons a minute flowing out of B, and 3 gallons a minute of fresh water flowing into A. Model the amount of salt x1 and x2 in tanks A and B respectively. So the rate of change of salt in tank A will be a function of not only the amount of salt in tank A, but also the amount of salt in tank B. So we'll have a dx1 dt will be a function of both x1 and x2. And likewise for dx2 dt. And remember that our way of doing this is to compute the input rate of salt and the output rate of salt. Let's label a few things. So we have 4 gallons a minute flowing from A to B, and the concentration in that is x1 pounds of salt dissolved in that tank, and there are constantly 50 gallons in that tank. Notice that the net input and output are identical. It's a total of 4 gallons a minute in and then 4 gallons a minute out. So it stays at 50 gallons of water. So that's our pounds per gallon there. Flowing in here, that was fresh water, that's 0 pounds per gallon. Flowing from B to A, there are x2 pounds of salt in tank B, and again, constantly 50 gallons of water in it, because initially 50, and same input and output rate, 4 gallons a minute in, a total of 4 gallons a minute out, 3 plus 1. And over here flowing out, that concentration is also x2 pounds per 50 gallons. Okay, so dx dt, that's 3 gallons a minute in, times 0 pounds per gallon, that's this part. And now we have this other part flowing in, so plus 1 gallon a minute in, times x2 pounds per gallon of salt in that input part. And as always, we can do a dimensional analysis, gallon over gallon cancels out, and we wind up with just pounds per minute, which is this dx1 dt, that's pounds per minute. And then our output rate of salt, that's 4 gallons a minute out at a concentration of x1 over 50 pounds per gallon. Again, the gallon over gallon cancels out, and we just have pounds per minute. Okay, and simplifying this, that's negative 4 over 50 is 2 over 25 x1 right there, plus 1 over 50 x2. And then we can do the same analysis with dx2 dt. And following that identical kind of analysis, we wind up with another differential equation for dx2 dt. So we wind up with a system of differential equations, which we cannot solve for yet, but we will learn how to solve systems like this later in the course. Right now, we're just getting a taste for what setting them up is like. Similar to what we did in 1.3 before we could actually solve them, and then we did solve them in the previous 2 sections, and more. So this would be our system. This pair of differential equations accompanied by these initial conditions that initially there were 25 pounds of salt in tank A, and tank B was fresh water, 0 pounds of salt in tank B initially. And if we were masochistic, we could do this with 3 tanks as well. You would wind up with a system of 3 differential equations, all related to each other. And we are masochistic, so let's do this. I actually encourage you to pause the video and take a minute or 10 to see if you can set up the system, calling the pounds of salt here x1, x2, and x3 respectively. Go ahead and pause the video. Okay, first thing to do is label our concentrations of salt in all of these pipes. So this pipe up here, it says pure water, that is 0 pounds per gallon. And actually the very first thing we should have done is make sure that each of these is constantly 100 gallons. Otherwise we wind up with a problem where the tank water level in 1 is decreasing, and we would need to account for that. But as we can verify, a total of 4 plus 2 is 6 gallons a minute in, that's 6 gallons a minute out, so that is constantly 100 gallons, and likewise for the next 2. So this pipe has x1 pounds of salt per 100 gallons. This pipe here, that's going from tank B, and it has x2 pounds of salt per 100 gallons. This has also x2 pounds of salt per 100 gallons flowing out of tank B. This one has x3 pounds of salt per 100 gallons flowing out of tank C. And this one is also flowing out of tank C with also x3 pounds of salt per 100 gallons. And now we can begin to set up. So dx1, what is the change of salt in tank A after a microsecond? Well, it's salt in minus salt out. The salt in, we have 0 pounds per gallon times 4 gallons a minute times dt minutes. Let me make a note. I realize that over here, the way the book teaches it, it talks about rates to begin with. Well, the way that I have taught it is just the dt's are on this side to begin with, and then we divide by dt. It's the same thing, really. I just break it up into a precursor step. So the amount of salt that came in from this pipe is 0, naturally. That's just spelling it out. But then there's also salt coming in from this pipe. And from that pipe, we have a flow of 2 gallons a minute times x2 pounds per 100 gallons times dt minutes. That is our salt in. And now we need to subtract, that's a big minus sign, subtract our salt out. And where is the salt flowing out of tank A? Just in this pipe. That is 6 gallons a minute out times x1 pounds per 100 gallons times dt minutes is how long has passed. So that is our salt out. So that's our equation for dx1, and now we can divide both sides by dt, and we wind up with our first equation. So if we simplify that, we divide both sides by dt. Okay, this whole guy is 0. This guy is a total of 2 over 100. That's 1 over 50 times x2, 1 over 50 x2. And then our salt out was this. 6 over 100 is 3 over 50, and then times x1. And that is our equation 1. And perhaps we should have first done dimensional analysis, made sure it all made sense. And we did indeed get only pounds on the right-hand side, which is the unit of dx1. Okay, so now we do the exact same thing for tank B and tank C. And for each of those, we'll wind up with another equation. As always, it'll be salt in minus salt out. Tank B has the most going on. There are 2 sources coming in and 2 sources going out. So the first source coming in, that's 6 gallons a minute with a concentration of x1 pounds per 100 gallons. And we're looking at a little time increment dt minutes. The units work out to just be a difference in pounds. And then our other source coming in is at a rate of 1 gallon a minute at a concentration of x3 pounds per, happening over a time frame of dt minutes. And then minus our salt going out. Salt going out is 2 gallons a minute out this pipe at this concentration, x2 pounds per 100 gallons. Big parentheses since we're subtracting this whole salt out thing. So also salt out is this 5 gallons a minute there at this same concentration over dt minutes. So fun. This equation involves all 3 variables. And simplifying this by dividing both sides by dt and multiplying through, like 6 over 100 is 3 over 50, we wind up with dx2 dt is 3 over 50 x1. Let's do the x2 part first to keep it in order here. So minus 2 minus 5 is minus 7 over 100 x2, and then plus 1 over 100 x3. And that is our equation number 2. And then we finally do it with tank C. I think at this point you get the idea. And we wound up getting dx1 dt was this. We got dx2 dt was that. And finally dx3 dt is that. So that is our system of differential equations. We'll learn how to actually solve systems like this near the end of the course, but that is the setup. And that does conclude this short section 3.3. Have a good one.